Good afternoon, this is Schweitzer, and this is a video on more Q versus K. We're discussing here the idea of what's called reaction quotient. You may be somewhat familiar with it, or it may be brand new to you. We're going to run through some examples of how this works. There are some previous videos that do talk about it and introduce it. But let's say we have run through two different examples. The first example is chemical reaction okay. And we're going to start with some initial conditions of, well, solid doesn't have a concentration, so there we go. Let's go with 0.5 mole per liter of this, 1.5 mole per liter of that guy, and D is 2 molar. With a K value that equals 500. Okay, so our first question is going to be, I want you to be able to, I'm going to leave a little room here for an ice table in case we want to use that. But first question is going to be write out equilibrium expression, the KC expression. Second one is going to be determine the reaction quotient. And then number 3 is going to be which direction will the reaction proceed to get to equilibrium. I wrote down K there because that's what we're looking for. Will it go that way to get to K, or will it go this way to get to K? Alright, so our first little discussion here is, now again, you can pause the video, try it out, see how you can do on these 3 questions. We'll have another one here. If you're not 100% yet, you can try this one with me and then try the next one on your own. Alright, so the Kc is going to equal the concentration of products over reactants, so the concentration of C, concentration of D. And then B will be concentration of B, and then that's it. We do have a squaring on this guy because of the coefficient of 2 right here. Okay, reaction quotient. I use this algorithm to just plug in my current values, which is going to be 1.5 times 2 divided by 0.5 squared, and this is going to give me 2 times 5, 1.5 is 3 divided by a quarter is 12. This is our reaction quotient. This is where we currently are, and will eventually, given time, will approach 500. So in this situation, which way will the reaction proceed? Well, we can actually figure out the exact ending point of where the reaction will be by just doing the algebra. I'm going to lose x, 2x of this guy. I will gain x of this one and gain x of this one. 0.5 minus 2x, 1.5 plus x, and 2 plus x. Now again, at this point I could say, okay, plug these guys into the expression, because I'm at equilibrium, I'll actually get that's the equilibrium conditions. So that would be 500 equals 1.5 minus plus x, and then we have 2 plus x, and then we have 0.5 minus 2x, and then this guy, b, would get squared. So at this point, we have more of an algebraic problem. This guy gets foiled, brought up, multiplied by the 500, move all these other guys over the side or foil it, and then you end up with what would appear to be a quadratic formula. Although it's not that difficult sometimes, well, I should say sometimes you end up getting into a cubic cube it, and then that gets the quadratic form will no longer work. But we're going to be losing, now in this case I cannot use my shortcut rule because the k is so large. In fact, a considerable amount, more than half obviously, is going to go over to products and stay there. So either way, at this point we would just need to use math algebra to solve this. Now I would never require you to do a quadratic in class. It's not a math class at this point. We're not testing that skill, but understand that that's how you would do it. So this thing will be shifting towards products because in this situation Q is smaller than K, and for Q to get bigger, as seen here, we need to lose reactant and gain product, and therefore the direction will shift to the right because this is smaller than this guy. And this is the typical way an AP curriculum would describe this. All right, let's try another example. All right, let's use all right, and in this situation our initial starting conditions are 0.5 mole per liter. We have 0.5 atmospheres, and I have 0.25 atmospheres of this guy. Same questions. We're going to leave some room for an ice table if we desire to do that. Question number 1 is going to be the Kp expression. Question number 2 is going to be reaction quotient. I want you to calculate it. And question number 3 is going to be, okay, which way are we going to go? In this situation, okay, you could pause the video, give it a try. The Kp is equal to the pressure of C squared, pressure of, in this case, B. We have the reaction quotient is just going to be taking my initial conditions and subbing in there. So I have, in this situation, 0.25 squared over, now I don't use A here. A is not here in the initial thing because it's aqueous. It doesn't have a pressure. So I can't use this guy at all, really. Now it has to be present, and we are going to lose some of it as we, or gain some of it as we approach equilibrium. Depends on which way we're shifting, but it cannot be used in this calculation. And this guy therefore is going to be 0.5, and this thing is to the first power. So do the math here. 0.25 times 0.25, so quarter of a quarter divided by 0.5, and your Q will equal 0.125. Okay. Now, in this situation, my Q happens to be bigger than my K value. Okay. Okay, so the K is quite small. This means that Q must get smaller, and for Q to get smaller, I would need to lose numerator, gain denominator, which is shifting towards the reactants. Again, that's the answer to all of my questions. I'm all done here. Again, a couple things to note about this. The size of the K value matters. As the K value gets bigger and bigger and bigger, we go more and more to products. And eventually it gets big enough, we might consider ourselves to be just at completion. Either way, depends how close we're looking at it accuracy-wise. But this is going to be, this would therefore be minus 2x plus x plus x. Note that now I'm going to the left, losing product, gaining reactant. No problem here. 0.25 minus 2x, 0.5 plus x, and 0.5 plus x. At this point, we could say, okay, I got 0.0015 equals 0.25 minus 2x squared, all right, and I have 0.5 plus x times, okay, and then be 0.5, well, in this case I cannot include this one because it's not going to be there, And there we go. So just one of them. And then at this point, multiply up, distribute. I would FOIL that out, move everything to one side, and solve with the old quadratic. Now that would give you the exact values of x, which then you could plug into your formula to know the expression, to know the exact amounts. Stoichiometrically wise, you could probably figure out how much of this is left as well. And that is where we'll stop for now. Thank you very much.